Hello! Today we're going to talk about Chapter 22, Inferences about Means. Now that we know how to create confidence intervals and test hypotheses about proportions, it'd be nice to be able to do the same for means. Okay, so just as we did before, it's all going to be based on the sampling distribution model. Okay, so the central limit theorem told us this, that we model it with our mean and our standard deviation. However, all right, we need that random sample and the true population standard deviation. That's an issue, okay? How are we going to get that? Okay, especially if we're just trying to just look at what the mean could be. Okay. All right, so unlike proportions, okay, that have a link, all right, means, all right, knowing the sample mean tells us nothing about the standard deviation. So we'll do the best we can, and we have an estimate, or we have a standard error based on our sample statistic. Okay, so now we have extra variation, all right, and now we allow for that extra variation so it doesn't mess up that margin of error and the p-value, okay? And the shape of the sampling model changes. The model is no longer normal. All right, so now we have to think about what our sampling model is. William Gosset, an employee of the Guinness Brewery in Dublin, Ireland, okay, just look at that face. He had a great job. He was happy with his life, okay, because he worked long and hard to find out what the sampling model was, because he wanted to make sure he could get the best and darkest brew, okay, and he had to make sure he did the right number of samples and whatnot, because it took a while to brew things, okay. So he worked really hard and he wanted to publish his statistics, but Guinness was worried about them, him giving away secrets, and he assured them that no, that's not what I'm doing, it's just about the statistics. So they agreed, well, okay, fine, you can publish it, but do it under a pseudonym, because that solved the problem. I don't know, whatever. But so that's why you might see it as student's tea, okay? Now, they model, form a whole family of related distributions that depend on a parameter known as the degrees of freedom, which is related to how many things are in your sample. Okay? So a practical sampling distribution model for the means, when the conditions are met, of course, the sample mean is this, and it follows a student's t model with n-1 degrees of freedom. You estimate the standard error by this. All right, so when Gosset corrected the model for extra uncertainty, the margin of error got bigger. Okay, so obviously your confidence intervals are going to get wider, your p-values get a little bit larger because there's more uncertainty, right? Think of it like that. Okay, so you're a little bit more unsure, so you're going to take a bigger guess. Okay, by using the t model, you've compensated for that. All right, in just the right way. Now, for the confidence interval, okay, you want to do a one sample t interval for the mean. So when the conditions are met, you have this confidence interval with your standard error being this. Now, notice this t star n-1, that is your, that's your critical value based on the confidence level and the number of degrees of freedom, and we'll get to that in just a second. Students' t-models are unimodal, symmetric, and bell-shaped. All right, but t-models with only a few degrees of freedom have much fatter tails than normal. Okay, again, you're making that margin of error bigger, you're a little bit more unsure. Fewer degrees of freedom, think of it like a smaller sample size. Okay, so that kind of skews your data out, okay, on both sides. All right, so as the degrees of freedom increase, it looks more normal. In fact, with infinite degrees of freedom, it's exactly normal. All right, things to know. So how do we find these t-values? Well, The t-values, you can do it by hand. There is a table that you'll be given based on either a two-tail probability or one-tail probability. Here you have your degrees of freedom. Okay, so you do your sample minus 1, and then here is your critical value. Okay, now let's say eventually this starts to start rounding and goes, I think, by 5s and 10s or whatnot. And let's say your degree of freedom is 32, but your table only has 30 or 35. Okay, well then you have to decide what to do there. I would round down because again, you don't want to decrease that margin of error too much or overcompensate. So I would round down, and you just pick the closest one on the table. Or you use technology to find it. Okay, you can use that inverse t function. Okay, using the area and the degrees of freedom, just typing it in there. So that can also give you your critical value. All right, so assumptions and conditions. Okay, so Gosset found the T model by simulation, all right, by testing it on a whole bunch of beer. Okay, worked out great for him. But years later, all right, Sir Ronald A. Fisher showed mathematically that Gosset was right. He needed to make some assumptions to make the proof work. Of course, we've seen these before. You have your independence assumption. So data values should be independent. They should arise from a random sample. It should be no more than 10% of the population, right? You've seen that. Now, for the normal population assumption, all right, we can never be certain that the data from a population follows a normal model. So we check the nearly normal condition. So check that the data come from a distribution that is unimodal and symmetric. So how do we check that? Either a histogram or a normal probability plot. The smaller the sample size, the more closely the data should follow a normal model. For moderate sample sizes, okay, roughly, the T works well as long as the data are unimodal and reasonably symmetric. Okay. For larger sample sizes, it's safe to use unless they are extremely skewed. Okay, so you always want to look at these things. Making a picture, making a picture, making a picture, all right, tells us far more about our data than a list of the data could ever do. Okay, so the only reasonable way to check the nearly normal condition is with graphs of the data. So either make a histogram, so unimodal, which means one mode, okay, symmetric with no outliers, okay, roughly, okay, it's not going to be perfect. You could also make the normal probability plot, all right, as long as it's reasonably straight, right, same way to graph these two things, all right, that's how you can see, all right, if it's nearly normal. Now, in the interpretation, that's where people get lost all the time. So if you ever read any kind of statistics in any article, which trust me, they throw statistics at you all the time, you should always not only look at their conclusions, but look at their data, okay? Because a lot of people mess up the interpretation. So I'm not going to sit there and say what don't to say, okay? I don't want you to remember that. I want you to remember what to say. So you want to say things like 90% of the intervals that could be found in this way would cover the true value. Okay, make it more personal. So in context, I am 90% confident that the true mean is between 29.5 and 32.5 miles per hour. Okay, you're confident that 90% of your samples, you would get this, okay? It would capture it. Now, let's do an example. So with coffee cups, here, take a second, pause it, read it, okay? Now, there is one way you can remember this. I found this, sometimes kids find it to be helpful. It's the oh, what's the word? Acronym? I'm asking like there's kids in front of me. I don't know. Remember the word phantoms. Okay. Phantoms is because you got a lot to list out. Okay. You want to make sure that you're going through the thought process. So P stands for parameter. Okay. What is your mean? What are you trying to, what are you looking for? Okay. What is your hypothesis? What are you trying to prove? What are your assumptions? Did you pass your assumptions? Name the test. Going to do a t-test on means. Our test statistic. This is how we do our value. Then we can obtain the p-value by using our calculator. You use the tcdf function. Okay, so we want the left-hand side, so pick a really small value, then that t-statistic, and then your degree of freedom would be 19 because there are 20 values, so n minus 1 is 19. We hit enter, we get our p-value. All right, M stands for make a decision. The p-value is low, so I'm going to reject the null hypothesis because that is very rare, so that the true mean amount of coffee per cup is 10 ounces. So, state the conclusion in context. There is sufficient evidence that the mean amount is less than 10 ounces. The machine is probably shortchanging customers, so we should probably adjust for something. All right, so here is another example. So a company has set a goal of developing a battery that lasts over 5 hours in continuous use. So tested 12 of these batteries. This is what we found. Is there evidence? Now you don't have to follow the phantoms. You could just list things out, but you have to make sure that you write everything down. So here is one way of writing it. You've got your conditions stated. Okay. Let's see, you have your mean and your sample standard deviation, what n is, what your degree of freedoms are, or is. All right, your hypothesis, your t-statistic, your p-value, and then state your conclusion. Since the p-value is greater than 0.05, we are going to, we fail to reject the null hypothesis. There's not enough evidence that the mean lifespan of the batteries is more than 300. Okay? So make sure you know that you're hitting all the points when you answer a question like this. All right, now for the test for the mean. So a one sample t-test for the mean. Okay, so the conditions are of course the same as for the interval. We test the hypothesis using this statistic, and the standard error is this. When the conditions are met, the null hypothesis is true. This statistic follows a student's t model with n minus 1 degrees of freedom, and we use that model to obtain a p-value. Okay, just like we were doing. Okay, but now with a mean. Okay, so pause it. Read it, see what you can do. Okay, so now we want to write the appropriate hypothesis. So that would be like this. Equal to, your alternative would be greater than. Find your mean and your standard deviation. Okay, you can either do it this way or use your calculator. Either way. I'd probably put it in my calculator and just do one variable stats. Find the p-value and explain it in context. So I like to draw a picture. We wanted it greater than. So we have our standard error, we have our test statistic, and we obtain our p-value. If the null hypothesis were true and the true average weight of these kinds of bags was 28.3, there's only a 1.6% chance that we would take a sample size 6 and obtain a sample mean of 28.78 grams or more. Okay, right? That was a mouthful, but that's from this 1.6% chance. So what is our conclusion? based on this very small sample, there is an indication that the average weight of bags like these is greater than advertised, so more. So that proves, not proves, but kind of justifies our alternative hypothesis. Okay, I gotta watch your words. Never want to say it with certainty. All right, here is another example. So take a minute, pause it, think about it. Okay, so does this provide evidence? All right, hopefully you thought about it. Now this is another way of writing it. I've seen kids write it this way. If you don't like what's the word I'm looking for? Equations or more like variables and things like that. This is more wordy. Okay, so this is for my more, I don't know, English language people, all right, my readers out there. Okay, so here is your null hypothesis, your alternative hypothesis, your conditions. Okay, so then we do a test statistic. Okay, so here we can denote it with simple notation. All right, but then we can describe what the numbers mean. So we perform a one sample t-test, and it gets us a p-value of 0.02. So that is a little over 2% chance. Okay, so there is evidence to well, we reject the null. So there is evidence to suggest the mean percentage of unpopped kernels is less than 10% in this setting. Okay, hopefully that makes sense. Now, you want to be careful when you say things like statistically significant, because that does not mean actually important or meaningful. It sounds really fancy. It sounds like, you know, that's top-notch, really, really important. But no, it doesn't mean that. Okay? What was the example in the book? Some insurance company on their prices said it was statistically significant increase in their prices, but it was a $10 increase and they normally pay $1,000. Okay, it might be statistically significant, but if I'm paying $1,000, $10 is not a big difference. Okay. Now, if they were talking about Hulu prices and they're going to jump that up $10, then yeah, you're going to be hearing from me. Okay. All right. It's all about context. Okay. Just because it's statistically significant doesn't mean it's meaningful. So don't get caught in that trap. All right, now hopefully this all sounds familiar. So your intervals and tests, confidence intervals and hypothesis tests are built from the same calculations. So again, they're complementary ways of looking at each other. Remember, a 95% confidence interval matches a 0.05 level two-sided test of this data. Okay, so hopefully that all sounds familiar, right? 1 minus c over 2, right? For when it's one-sided. All right, now how do we figure out the sample size? It's somewhat similar to what we've done before, right? We want to just solve for n in our margin of error calculation. However, there's an issue because we don't know some stuff. So we can use S from a small pilot study. All right, we can also use Z star instead of the necessary T. Okay. The sample size calculations are never exact. All right, the you find, the margin of error you find after collecting data won't match the one used to find n. Okay, won't be perfect, so don't get hung up on that. Okay. This is just a way before you start collecting your data to make sure that your sample size is large enough to give you a good chance of being able to tell what you want to know. Okay, it's just a way of checking yourself. So it's not going to be perfect, but it gives you like a ballpark, right? Think of it like that. Now, if we only knew the true population mean, would we find the sample standard deviation as this? But we use the mean instead of the population, and that causes us a problem, right? Our statistic instead of our parameter. When we use that instead of this to calculate S, our standard deviation estimate would be too small. So what's nice is how we can compensate for that smaller sum is dividing by n minus 1, which we call the degrees of freedom. Okay? All right, things to look out for. Don't confuse those proportions and means, and look out for ways to not be normal. So multimodality, all right, so that's multiple modes. Okay, it fails if it has 2 or more modes. Beware of your skewed data. If it's very skewed, try re-expressing the variable. Okay, and always set your outliers aside. Remember to report these outliers individually. You have to name them. Okay, talk about them. Don't just ignore them. Watch out for your bias, which we can never overcome the problems of a bias sample. All right, that's just, you have to know that. All right, make sure your data is independent. Check for random sampling and the 10% condition. Don't forget your assumptions and conditions. Make sure that the data are from an appropriately randomized sample. Interpret your confidence interval correctly. Many statements that sound tempting are in fact misinterpretations of a confidence interval for a mean. Okay, pay attention. All right, get that right. Okay, so a confidence interval is about the mean of the population, not about the means of samples. Individuals in samples or individuals in the population. Okay, so it's about the mean of the population. That's what you're focusing on. So watch what you say. All right, and this is everything we've learned. Hopefully chapter 22 isn't too bad. But if you have any questions, again, please come see me. Again, I know stats hard. It's weird. Come talk to me.